dichlorocyclobutane, 1-bromo-3-isopropyl-cyclohexane, and dichlorocyclopentane. All of these questions, if you're asked how many isomers of these are optically active or how many stereoisomers there are, the process is going to be the same, which I'll demonstrate here. Now there is a hack. So personally, I don't like using the hack too much unless you're like really out of time, like, and then you just want to check your answers. But I want to show you how to draw out all the possible stereoisomers and analyze it from there on. So dichlorocyclobutane, how I like to start is, I know they can be on the same branch, but I just like to start with them on different branches, and I like to start with them with different wedge and dash bonds. So then that tells me that there can be a mirror image, and therefore these two are enantiomers. Okay, don't overthink this. Now the other stereoisomers possible is going to be the diastereomers of these enantiomers. So you are going to flip a wedge into a dash or a dash into a wedge. Personally, I highly recommend switching the dash into a wedge because it saves a lot of issues later on when you're doing your RNS assignments. So this is going to be like that. And then you might think, okay, let's draw the mirror image, but you're going to find the mirror image is the same thing. Okay, even if you don't find it's the same thing, which happens a lot, you just need to recognize when you're given a problem that you're given two identical substituents, two identical groups. Let's change the color, something more visible. Especially if you have a cyclo compound and you're given two of the same branches, like two chlorines here, you're gonna instantly know that there's gonna be a meso compound. So this is our meso compound, which means its mirror image is the same thing as the meso compound. The meso compound has chiral centers, but it is overall achiral due to the plane of symmetry. Okay, don't overthink this. This is a little box that you need to make on your test to prove how many stereoisomers or whatever there are. Now the other, like, a little thing that they want you to know, but I think it's really important to draw these things out, is that the other way to look at this is there are two chiral centers here, right? So you'd say to yourself, n is the number of chiral centers, so therefore there's a maximum of 4 stereoisomers, okay? But this is maximum. There can be less. And that is a cue. When you see two branches identical, and there are only these two branches on the cyclo compound, you're going to know there's going to be possibly one meso compound, so that instead of having 4 total stereoisomers, you're going to only have 3, consisting of that one meso and the 2 enantiomers. Okay, so this is like, you gotta make this your intuition. Gotta know it. Okay, so next time when you see dichloro or di something, cyclo something, you're gonna know, okay, I'm not gonna get 4 stereoisomers, I'm gonna get 3 because one is meso and the mirror image of the meso doesn't exist. Now, some other things I need to note is, if you're given another compound, like let's say they're not asking you how many are optically active, and let's say they give you a larger compound like cyclopentane, so once again, I can tell that there's going to be one meso compound, so instead of 4 total stereoisomers, there's going to be 3. And the thing is, if they're asking you for the total number of isomers, stereoisomers included, you would figure out that there's 3 stereoisomers here, but there can also be the constitutional isomers, where there are different linkages. And this also has 3 stereoisomers, okay? And another constitutional isomer could be this, right? But this is not chiral. This has two of the same groups bonded to the carbon. This is achiral. All right, so also I need to note, if you are ever tempted to say that this could be something like this or like this is wrong, okay? Do not think, when you see two branches on the same carbon, you can't say cis or trans for them because this is a tetrahedral shape. So you can't be having two wedges, okay? You can't be having cis and trans. It's just a tetrahedral shape. So when two of the same substituents are on the same carbon, there's only going to be one possible isomer for that position. Okay, so you don't think that there's going to be cis or trans when they're on that position. So which means if we were given dichlorocyclopentane, the total number of isomers possible is 3 plus 3 plus 1. That's 7. So I hope this video was helpful. If it is, make sure to drop a like and subscribe.